Okay, so welcome to this tutorial. Here the idea is to show you how to define lean-on bracing on a bridge, also to show you how to define skewed supports, and finally how to apply temperature loads in Embrace 3D. So if we go to this features form, you can see that we've got skewed supports and also thermal loads here. We do have wind loads, that's something else, but this is not really the purpose of this tutorial today. The main purpose is about thermal loads and lean-on bracing. We do have also special DOF fixities. This is really how you define skewed supports on the first support line. Okay, a positive angle means that girder 2 is located away in this direction in the y-axis. Okay, so this is what we have here. We have a straight bridge, and the skew angle here is equal to about 34 degrees. We have 4 girders. Spacing is 10 feet. These are the stiffener locations, so these are entered again either manually or copying and pasting data from Excel. We have 7 cross frames for each bay. Okay, and so this is the important point here. 0 here means that we have full cross frames, and 1 means that we have lean-on cross frames, meaning just the top and bottom chords, just these 2 chords. We do not have diagonal chords. We can apply a multiplier of 65% if we want to. That's not the point of this tutorial. This is something we would like to do for fatigue analysis or live load analysis. Okay. And so as you can see, the lean-on bracing pattern changes as we switch bays. We have 5 special fixities on girder 1, 2 on the other girders. The idea here is to have just one support, which is a pin support. So on the first girder at 0, so at abutment 1 on location node number 2, so the bottom flange node. And here at the end, we are just restraining the transverse and the vertical displacements. And for girder number 2, we're just restraining the vertical displacement at both ends. So no transverse displacement, okay? We are using this form because otherwise the default pin and roller supports would apply a lateral restraint. So here we prefer to have just vertical restraints, and the idea is to be able to have to allow the bridge to breathe under thermal expansion or contraction. And here again we are defining thermal load. So the idea is to see how the bridge would expand or contract under thermal load. So we are really taking care of the restraints here. The restraints have a huge impact on the thermal loads, on the behavior of the bridge under thermal loads. We don't need to store the reference points. Okay, this is a model that's already run, but again, as I say in every tutorial, if this is the first time you get to this form, you do have to click on it. And also every time you change the brace points, you also do need to click on it. The mesh size is equal to 2 feet, okay, which is pretty standard. We have just one profile, okay, for simplicity here. So all the segments have the same profile. We have just one stage where all the girders are fully active. The girders, of course, they are here all activated, okay. We're not studying the effect of maybe leaving certain cross frames out before the analysis. We have this wind load here. This is one way to apply wind loads. So maybe you would subject girder 1 to pressure of 35 psf acting orthogonally to the girder. And here is the form for the thermal load. So we have coefficient of thermal expansion, which is the standard one, the standard value for steel, 1 thermal loads, and we're applying a uniform expansion, so a positive gradient of about 30 degrees. So here again, we're not turning on the wind load. We're just applying the thermal load here, which is applied on all the girders. And to be absolutely thorough in my explanations, Embrace 3D does not allow at the moment to apply a thermal gradient, but only to apply uniform expansion or contraction. Okay. We can click on run or look at the results already, but this is a very simple model, so we may just run the analysis again. as you can see, these are the full cross frames and these are the lean-on braces, so just top and bottom chord. We can zoom out maybe. Let's move the bridge a bit. We can see the plate thicknesses. Again, this is something I always check. Okay, and now let's look at the linear elastic solution. Okay, so under pure thermal expansion, here the maximum displacement, we have the pin here. Okay, so as expected, this point does not move. This is as expected. But here, the maximum displacement would be equal to about 0.5 inch. Let's check the displacement in the longitudinal direction. Of course, this is the governing direction. And let's also check the one in the transverse direction. And this is quite interesting, okay, because we are just defining vertical restraints here. So as expected, the bridge is free to move in that direction. And remember, the cross frames also are subject to that 30-degree expansion. So there will be an expansion in the transverse axis, which is tiny, granted, but which does exist. We can look, of course, at any other results. So let's check, for example, are we expecting any stresses? Well, no, we are not, because the bridge is free to move, it's free to breathe. Okay, so I hope this tutorial was useful to look at skewed supports. You can see the skew here, and we can maybe go to a top view and look at these skewed supports. Okay, 33-degree angle. And this tutorial, I hope, was also useful to explore thermal loads as well as lean-on bracing. And of course, this is by no means a way of saying that, hey, for thermal loads, you need to have lean-on bracing. Okay, this is absolutely independent. Lean-on bracing is more useful for cross-frame design in a way to provide just enough stiffness to not attract too much load in those cross frames to keep their sizes to reasonable dimensions. Okay, but for thermal loads, there's not a clear benefit in any form. So this is it for this tutorial. Again, stay tuned for further tutorial on plate girder and tub girder bridges.